Hello, everyone. Welcome to our webinar. Thank you for joining us. Today's webinar will be on the performance consideration for the design of ground improvement systems based on rigid inclusions. Today's presenter is Augusto Ucurelli, who is a principal engineer with ITASCA in Minneapolis. He has a background in soil mechanics, numerical modeling of geotechnical processes, shallow and deep foundation design, soil improvement, slope stability, mechanized excavation, conventional tunneling in urban areas, deep excavation, and support structures in difficult environments. For today's presentation or webinar, we will be taking questions at the end of the presentation. This is a live presentation. There you will see there's a Q&A icon at the top of your Teams program. Just click on that and submit your questions, and we'll look at those at the end and answer them. Thank you. Augusto.
Yes, good morning, everyone. We can start, and I put together this material from different projects that I had the opportunity to work in the last, I would say, 3-4 years. The focus is going to be, as mentioned, the analysis of this complex system using numerical method. We are not going to touch today into any of the simplified procedures that are currently used, maybe as a preliminary tool, or even in other circumstances. We're just going to focus on numerical analysis and structural interaction. So first slide, we are going to have a couple of slides of main takeaways so that it kind of set the stage for the main topic we are going to touch. I already mentioned that we are not going to focus on simplified analysis that are essentially based on force equilibrium. Personally, I think that way overused and obsolete for most of these analysis cases. The problem is that there is no strain compatibility, as mentioned in the second point. So you only have a measure in terms of forces, but nothing in terms of strain mobilization and strain compatibility. There is, in terms of general, I would say, approach, in my view, there is too much focus on just analyzing one metric, which is the global factor of safety. Everybody's asking, what is the global mechanism? What is the global mechanism? But in reality, in this type of complex system, there is typically a weak link or a configuration in which several weak links are connecting together, starting with a smaller mechanism that then tends to propagate, depending on the strain, that are mobilized into a more elaborate and global mechanism. So the focus on the global mechanism could be sometimes misleading because we are missing some of the details. And this is kind of ties in with the other comments. This focus on one single metric as a single number doesn't really tell much about how the system is actually working. Even if we know that a factor of safety is 1.5 or whatever number we have to accomplish, we don't typically, with simplified analysis, we don't really have a feeling for what amount of displacement actually theoretically is. If we do just limit equilibrium, that would be infinite. And so it doesn't provide information on in any way or shape or form for the performance. Rigid inclusion, there is also, in terms of rigid inclusion analysis, those are wonderful, I would say, elements specialized for vertical control settlements. They tend to do a relatively poor job in the horizontal direction, unless some sort of a mitigation or additional constraint are added to the system. The rigid inclusion, even if we reinforce them, it doesn't really change the stiffness of the system in the horizontal direction. It might change a little bit the ductility and the bending capacity, but overall, in terms of performance and deformation in the lateral or horizontal direction, they are not doing a great job. Also, another topic that is when you have large extension of ground improvement in seismic condition, it tends to change also the local response. Essentially, you would get a higher acceleration that is brought up into the superstructure when we may modify the soil stiffness using this type of improvement. Okay, so this is just a cartoon view of our typical configuration for supporting ground improvement, MSC wall, concrete faces is typically organized. And I'm kind of emphasizing here again that the main focus of this system should be toward the horizontal deformation control. The vertical settlement are typically covered, satisfied. There isn't really much of an issue. Most of the time, when the system fails or, let's say, is not performing well, is because there is some problem in the horizontal direction. Also, this system, I use the word system because it is a system. It is not, I would say, conducive to any, let's say, deeper consideration if we analyze the single component on its own, like, for example, the column on its own, the MSC wall on its own, and kind of a split and parcel the various components and analyze them separately. We need to analyze the full system globally to see how the various components of the system are actually exchanging forces and so on. Okay, so the main ingredient of this type of support, we're going to touch base on each one of these very quickly, and then we're going to go to some of the project. Of course, we have to model the soil. Typically, the constitutive model for this type of analysis is the plastic hardening soils model, soft soil creep. For dynamic, the P2P sense. The way I use the calibration for the property determination is through CPT test. Typically, in this type of soil, the CPTs are available. Much less emphasis into the lab activity. As far as the column, typically those are modeled with embedded pile element. Can be reinforces or not reinforced. There are several layers of complexity in terms of modeling the column, as we'll see later on. Typically, there are other structures, either in the LTP, load transfer platform, or inside the body of the fill. Typically, these are geogrids. We're going to touch on the issue, quote unquote, when we combine these systems together. And then the stage construction also sometimes is important, especially when there are, let's say, material that are draining at a different time scale. Sometimes it's important to also consider the consolidation processes involved. And finally, the strength reduction factor analysis provides let's say, a more comprehensive way to investigate local, global, or multi-complex failure mechanism. So yeah, the constitutive model, as mentioned, those are largely in the industry. The plastic hardening small strain is widely worldwide recognized. There's an extensive amount of literature. There are a few links there to our website in case you want to investigate. There are other alternatives like soft soil, North sand, but are less common. P2P for dynamic analysis, and again, properties are as we will see later on, determined from CPT test most of the time. So kind of provide a framework for how to determine the soil mechanic characteristics using CPTs. I'm just showing a few examples here of application in which I've used the CPTs correlation to directly feed the numerical model. In this case, it was just a simple 1D column, as you can see on the right. But then use the CPTs to determine all the properties that are necessary for the constitutive model. Even, for example, in this case, I'm just adding the soil behavioral type into an extra variable to determine what type of soil, dominant soil is, for example, if it is a drain or undrained. And that is useful in this case, for example, when you have a consolidation process to detect those lengths of of material, more permeable material, because they have an impact on the consolidation time. Similarly for the shear wave velocity and also the G max. And now we are talking about the structural, the structural element that mimic the rigid inclusion or any type, let's say even pile foundation. There are different approaches that we can accommodate. The simple one is to just use an embedded element, linear elastic, and is coupled with those contact elements that you see on the cartoon figure on the left, in which we have a vertical spring and a slider, and also a horizontal spring and a slider. And there is a similar situation at the base of the pipe. So these are beam elements essentially, and those are contact elements. It is important to make a distinction because this is a question that comes up all the time. Those contact elements in the horizontal direction are not PY analogy. They are not analog to a PY curve. The reason is that in our numerical model, we have the soil, the zones model explicitly. When you do a L pile and a PY analysis, the soil is essentially lumped into a single spring. And so there is a fundamental difference in these two types of approaches. If you use the PY concept to calibrate those horizontal coupling springs, you get a much softer response because you have many systems in series, reducing the overall stiffness. In the vertical direction, the concept is a little bit different. In this case, we can kind of see those vertical slider similar to the T-zeta curve, because typically the vertical movement happen in a very thin layer of soil. And in order to capture the interaction at that scale, it would require a mesh density that is most of the time not compatible for a large project. So in the vertical direction, we could, let's say, see those coupling spring similar to a T-zeta curve, something, a localized failure. For the base, it could go rigid, elastoplastic, or as we will see later on, use a shell element to capture the size of the column or the pile. So the element itself can allow for nonlinearity. This would be a simple approach in which the pile element is made of a beam that can accept a plastic moment and also an ultimate shear force. And this diagram is just showing the classical truss bending diagram and the truss shear diagram that can be coupled inside the element so that the plastic bending moment would be updated during the analysis as a function of the current axial force that we have in each element of the pile. This is a second type of approach, a little bit more elaborate. Now with Flat 3D version 9, we have a nonlinear element. Essentially, you see in the lower portion that is a pile with all the Gauss point for the integration of the stresses in the cross section and come up with the stress resultant. But there is no steel cage, there is no reinforcement. In case we have to add the contribution of the steel cage, I had two piles at the same time that shares the node. One is the concrete pile that follow the nonlinear constitutive relationship. Either can be simulated with a more Coulomb, and now with a more Coulomb material at Drager-Prager, but there will be other development in the future. And then coupled with that, on top of that concrete pile, I added the NM cage or the steel cage as a pile element that followed the truss bending diagram of the cage itself. I tested this system multiple application and it works very well, and it gives you a clear separation between the contribution of the concrete and the contribution of the steel, and being able to capture, let's say, a little bit more accurately the response of the structure. Then the final approach in some cases where especially there are large diameter element, like in this case, this was a 2.5, 8 feet diameter shaft. for landslide mitigation. In this case, the best way to do it would be to just model the plain concrete with zones, so considering the volume, and then include also the steel reinforcement so that we will be able to capture, as we see in the lower right, the formation of a plastic hinge at the contact between the soft material and the stiffer material. Once we reduce the strength, we see the buckling of the concrete on the compression side, and also the failure of the steel in the tension side. So this provides us sort of the three approaches, from the simpler one, in which we're just updating the bending moment capacity as a function of the axial force, the intermediate one, in which we have two piles, one nonlinear pile for the concrete, and the other one is a nonlinear element for the cage, and then the full explicit geometry for situation like in this one. Okay, let's talk a little bit about the other potential elements that are in a system that reinforcement. Internal reinforcement could be made with geogrids. Typically, geogrids that are used for reinforcement, they have a machine direction and a normal machine direction. Typically, the machine direction is the dominant one in terms of direction. So the way this is a model essentially as a net of cable, in which the cables are accepting the properties in the machine direction and in the normal machine direction. There is a links that transfer, let's say, the normal force in the node, and then also the shear capacity in terms of pull-out force. Note that at the bottom here, what I'm showing is a typical diagram in terms of force strain for a geogrid. You see that geogrid typically breaks for, let's say, 8 to 10% strain. And that is one very important aspect that needs to be considered, because 10% strain to mobilize those forces is most of the time incompatible with concrete, steel, and other component of the system itself. So in many cases, we tend to, especially when we adopt simplified analysis, we apply the full force available for the geogrid in our simplified analysis, without realizing that in the force that becomes available at 1 or 2% strain, which would be compatible with a service limit state for the structure, is much, much less. And then you see a loss of performance or other issues because this configuration or this contrast in terms of stiffness and strain compatibility is not adequately considered. Okay, now let's go and start talking about the project. So we have discussed a little bit the layout. We have discussed a little bit the component in terms of constitutive model, structural element, and other geogrid aspects. So this is one project that I did recently for the Minnesota Department of Transportation up north in Duluth. It's called the Twin Portings Exchange. Okay, this gives an overview of the modification, as there were essentially a complex intersection built many decades ago that needs to be modernized, and in those bridges were essentially eliminated, and the decision was to go for a fill area. And then considering the nature of the soil, which was a very poor soft soil, decided to go with ground improvement. And there were probably 7,000 columns. There are a bunch of information in the presentation. I'm not going to get into the detail. But the idea here that you can see on the right, the large intersection was essentially the converging point of all these bridges and all these embankments. So the model that we developed was, you see in the right corner at the bottom, was the full intersection. Instead of going for smaller model, bridge 903, abutment A, B, and C, we would end up having 12 different models that were not communicating together and would not have been able to give the whole picture. We decided to go with one single model that has all the structure, all the main bridges, all the foundation, retaining wall, and everything that we will see later on. It's not that more difficult than build many little model and try to have them to work together. Okay, as usual in any analysis, we need to start from the subsurface, and what we are showing here is a sort of a cross section and a general overview of the 3D subsurface condition. And those little stick at the bottom, in the lower portion of the figure, those are the boreal and CPTs. As you can see, there were a lot of investigations, and we tried to put together a 3D model of the subsurface conditions because there were, for example, sand stiff layers that would not have allowed the columns to go through them. So knowing these detail in terms of subsurface condition was essential in order also to come up with a reasonable estimate of the quantity and therefore cost. The process of feeding the model is the same that we have discussed. I'm just showing a few CPTs profile typical of the stratigraphy, but essentially typical profile CPTs feed the flat 3D model with all the property that we need in terms of constitutive model relationship. This is the only slide with a few equations. I just wanted to emphasize what are we doing here in terms of how to transform the property from the CPTs to the plastic hardening constitutive model. First of all, the reference value that you see circled in red, those are not constitutive property model. Those are just parameters. The way I do the calibration is to focus on the E50 and the ER loading, reloading, and the E odometer when it's pertinent. Because those are the properties that we really need to estimate, and then reverse the formula to feed into the constitutive model the reference value. So I usually start from the CPTs, determine the shear wave velocity. It is not available directly. From the shear wave velocity, we determine Emax. And then from applying some divisor or some factors, we determine E50 and ER loading, reloading. And there is a relationship of this factor between the soil behavioral type. This factor tends to be lower when we have a soil behavioral type that is closer to a clay, let's say in the order of 3, 3.5, and then tends to be higher, 2.5, 3, as a divisor when we are close to a sandy layer, so a behavioral type in the order of 1.8, 2, or something like that. The advantage, or one of the important features of the plastic hardening, but also the soft soil creep and others, is that we need to have, they allow for volumetric hardening. More Coulomb does not have a volumetric cap, so all the deformation that are happening in the volumetric side are not correctly captured. Okay, 3D model geometry. This is again an overview of the 3D model. You see on the left, bottom left, those are the columns, model explicitly each one. And then on the right, we have the stratigraphy and the two main longitudinal and transversal sections that we're going to see later on in the presentation. Yeah, so let's go. These are, I'm showing a few of the displacement. The displacement in the longitudinal direction. There is a cutoff, but 1.2 to the minus 1. Those are 120 millimeters, so the unit are in meter here. And the other one, the gray and red, is showing the horizontal displacement. Keep in mind that, as I was mentioning at the beginning, in order to improve the lateral stiffness, we put inside the embankment, you see on the upper left corner, internal rebar inside the embankment itself. These internal rebar engage are made of steel. Okay, so once the embankment wants to expand laterally, essentially is constrained by this internal rebar, and this really helped to control the lateral deformation for the column that would have been essentially incompatible without these rebars. And the Geogrid would have not been able to provide a decent control of the horizontal deformation. There are some few pictures later on that we will see. Okay, so we are going to show, so the upper slide is showing the moment utilization in the column, which is essentially the ratio between the moment exerted and the moment capacity, which is a function of the axial force. We have a few spots in which we are going up to 0.9, and there are a few regions in which we also had a little bit of reinforcement at the top. But without the horizontal rebar that we see in terms of stresses mobilized in the lower portion of the picture, the situation would have been not compatible. Even adding full reinforcement or heavy cages, those vertical columns would have been suffering a lot. Instrumentation, there were several instrumented sections with a bunch of different monitoring systems from shape array, horizontal and vertical piezometer and whatnot. Okay, so this is the shape array monitoring that is showing in the central section what was recorded during time. And this was probably a year or something after construction. And what was determined during the analysis. You see that there is a very good correspondence between the 120 millimeter measured on the left and the one calculated on the right figure. So all in all, the procedure, and this is not in this case, but I've seen this also in other experiences in which I go through this CPT process calibration, feed the model. You get a very good, let's say plus minus 20%. Obviously, this case was a little bit better than usual, but it gives you a good estimate of final expected performance. Okay, a few pictures of the construction. We see the pile cap. So the column on the upper side and the pile cap for on top of each column. These are just concrete pile cap with a little bit of reinforcement. So these are a picture of the rebar that I mentioned earlier inside the fill to control the horizontal displacement. You see that there is a plate at the end that kind of attempt to engage a little bit of passive resistance, but the bars are not connected to the wall. So there is the reinforcement of the wall that is connected to the wall, and this is a completely independent system that engages as a function of the lateral deformation of the fill, engaging the axial stiffness of the rebar. Okay, RSS, this is a different example, also from the same project. What I want to show here is how to optimize and the benefit of this horizontal reinforcement in the column design. So this is on RSS. We see in the circle, there was a problem of protecting the toe of this RSSI. And so there were the different alternatives. One alternative was to extend the columns to the left. But those columns essentially don't have significant axial force. So the contribution that they can bring in terms of shear and bending is very modest. Okay, so here's the situation in which we model the embankment, the reinforced soil slope, and also the column extended all the way almost to the edge of the little berm at the toe of the reinforced soil. This is showing a detail of the model. You see in this case at the top, I put a plate, a shell element that considered the size of the column. I model also the layer of the geogrid, as mentioned earlier, and also the geogrid inside the LTP, considering the mechanical properties that we had. And so here's what happened when we just don't consider this system. You see on the left, all the columns are essentially becoming plastic mechanism. You see the kink in the deformation of the column. The bending moment exceeds the capacity because we don't have axial force over there, and so the bending capacity is very small. And we see also that the plastic hinge formation really tracks well with the strength reduction, in which we have the shear failure mechanism that goes and plow over the top of the columns. Now the alternative was, okay, what would happen if we had horizontal rebar in the lower portion of the embankment, like we did for the larger embankment? If we have this number 10 rebar, 20 meter long, see what is the benefit. Now, and also on top of that, eliminate, so the trade-off was to eliminate the side column underneath the berm, which we were doing absolutely nothing, and substitute those columns with this rebar. Now the displacement are much, much less, is in the order of 50 millimeters, the displacement at the toe. And now we see that we don't have that bending failure anymore. The moment utilization stays below 0.9, which is fine. And this is the stress in the rebar. So essentially what we're doing here, we are specializing two systems. One is the column, which is highly functional for vertical settlements and vertical displacement control. It is very poor in terms of horizontal control. So we are adding a system or a component to the system that is highly specialized in taking horizontal displacement. And so the two, let's say, support system are collaborating together, one taking the vertical and the other one taking the horizontal, even if they're not connected at all. Okay, this is the final project. One of the issues that we had in this project is that the LTP was not even connected all the way through. You see there is a lower section of the roadway that is significantly below ground, and then there is another one that is elevated. So the LTP was not connected. And as usually happens, the poor soil was on the right side. So we have where we have to go deeper. So this was a combination of the main cross section that we used essentially was 35 meter extended in the out of plane direction. And we built in order to capture all the structural components. So the concrete panel of the MSE wall, all the steel stripes, and the geogrid inside the LTP, the column at the bottom with the different diameter and different spacing. So the full system, and also including the construction stages. Okay, so this is showing a picture from that shows the detail of the column with the shell at the top that takes into account the physical size of the column itself. It is important in this type of application because if you just have a link at the top of the column, it tends to just grab one zone, and so you have a very concentrated stress. On top of that, if the zone is made of, let's say, more Coulomb material, for example, it will yield at some point. So when it is not even able to correctly capture the load transfer that happened at the top of the column and the arching that would happen naturally inside the embankment, that aspect would be completely missed. So what happened in this case? This was the base case. You see that the displacement on the taller portion of the embankment is very high, 230 millimeters, not acceptable and not functional for the roadway. Well, on the other side it was 55 millimeters. Just the same thing by showing the displacement at the bottom. Okay, and this is the form shape of the column. Of course, on the right side, those columns are way too overstressed, and even adding the reinforcement, they would not be able to control the bending moment, and most importantly, they would not be able to control the horizontal deflection. Okay, this is showing the whole system combined. The other issue is that also the reinforcement of the MSE wall was overstressed at the bottom. So the lower layer of the reinforcement of the MSE wall were getting close to yielding, and that was also not acceptable. So the solution, again, here was to add 2 layers of rebars in the middle of the embankment, completely disconnected. As you can see here from the figure, there are plates at the end that engage in passive resistance in order to mitigate the horizontal deformation. We're going to have a bunch of here. And so this is the stress inside the rebar, totally compatible. We are in the order of 200 megapascal, so totally acceptable. And finally, the displacement. Remember, the original displacement without this horizontal constraint on the right side was 230 millimeter, and now we have a displacement that is in the order of 40 millimeters, so an order of magnitude lower, and this is totally compatible with the functionality of the, and we didn't have to put any reinforcement on the columns, and also the reinforcement of the MSE wall was much better from a stress standpoint. So just a summary of what we have discussed this morning. When we are dealing with this complex system in which we are combining different components that engage at different level of strain, simplified methods do not provide, I would say, an answer, satisfactory answer in terms of understanding how the system works. Strain compatibility is essential. Rigid inclusion works very well for controlling vertical settlement, but we need most of the time to add some other element or some other system in order to improve the horizontal stiffness of the system. I guess we already mentioned this this point. I guess future projects we need to prioritize performance-based and strain compatibility over just targeting a single number represented by the global factor of safety. It is not informative enough. That is the end of it. So I'm available to have any question or any clarification.
Great. Thank you, Augusto. If anyone has any questions, if you could please type them into the Q&A tool. There's an icon at the top of the screen. You just type in your question and submit it. Please feel free to use the chat as well. Okay, we have a question, Augusto, in the chat.
Yeah.
Can you see it, or would you like me to read it?
I don't see it.
Okay, I'll read it. In the presentation, it moved. It was shown that the cage reinforcement and concrete pile properties were assigned separate elastoplastic material models. Can plastic rotation outputs still be obtained in the same way in this case?
The plastic rotation, plastic strain. Plastic strain, yes, plastic strain can be obtained. So for the concrete, you have the possibility to check what's going on in each Gauss point of the integration system. For the other pile element that represents the cage, that is the same as before, so you can obtain your plastic strain if you go over the plastic limit that you have set.
Great. In the FOC 3D web manual example, laterally loaded pile, I tried to test the pile elements with plastic integration with the more cool model, but I could not obtain reasonable results. Are there any specific considerations I should be aware of when doing this? Maybe.
Well, it's not for me. It's not for me to, let's say, speculate on what you did in your model. Typically, what I would do is, if you're using more Coulomb for concrete, you have to go through, let's say, calibration process. So you have to use a strain softening in order to be able to capture the compression side, go up to the peaks, and you do that usually implementing a table. So essentially changing the cohesion as a function of the plastic strain, and you do the same thing for the tension. In a later version that will come in the future, there will be the concrete model available for this type of analysis. So we wouldn't need to go through this calibration process, which is quite tedious and impractical. So in a later version, there will be a concrete model to solve all these issues. I'm sorry, I cannot say what actually. I've used this concrete model multiple times. As I was showing even in the presentation, I didn't have any particular issue, so I'm not sure what could be the problem in your case.
Okay, thank you, Augusto. Please explain how you selected the different structural elements. I guess a pile versus a cable versus.
Oh, okay. Well, I mean, if we're talking about the rigid inclusion, those are essentially elements that can take axial force, bending, and shear. So the selection of the structural element follow the idea what kind of stress resultant is the most important one. For example, for the geogrid, I don't care about what kind of a bending moment could happen in a node of the geogrid. That is completely irrelevant. So a geogrid is modeled with a cable element, okay? Because I'm only interested in the axial component. And I have also the possibility to specify or to a different strength in compression and tension. A geogrid only reacts in tension and doesn't have any compression. So that's why with the cable element, I have the possibility to play around and specify what kind of a response I want from the element. For the rigid inclusion, the pile element for a simplified analysis is the best one because it allows to capture the axial, the shear, and the bending, and somehow also you can also set some limit in terms of structural capacity with the three method that we have shown before. There are other elements, for example, for the walls. The wall face was linear. And in that case, each panel was modeled independently because those panels is not a continuum concrete wall. Those panels have joints, are separated, there are leveling pads in which each panel is sitting on top of each other. So you have to be able to capture those discontinuity because if you model as a single concrete element from the foundation all the way up to the elevation, you get a completely different structural stiffness, bending capacity, and shear capacity that you would get from the real discontinuous structure. I'm not sure if I answer your question, but essentially the selection of the element depends on how the structural element responds in the field.
Great. Just a follow-up question to that was how were the properties for the different structural elements determined?
Well, you need to know the material. If it's concrete, it's concrete. You need to know the UCS. From the UCS, a 28-day standard, you have an idea of the FCK, and from the FCK, you can calibrate the constitutive relationship for the 1D element. If it's steel, it's simple. The yielding of the steel and the elastic modulus. I don't know. It could be wood. Wood could be a little bit more complicated because it is a non-isotropic material. You have different direction. But in general, I've never been using wood in any type of application. If we stick with concrete and steel, the properties are relatively simple to get and calibrate.
Thank you. Next question. Did you compare FLAC 3D structural element moments to simplified software such as LPILE by imposing similar lateral displacements? And if so, how did this compare?
No. The simple answer is no, although I did several comparisons in terms of not for the single element itself, but how would you, for example, the implementation of the LPILE in a limit equilibrium analysis in comparison to a full numerical analysis. The problem with that approach is that even if we have LPILE, we don't know what is the displacement field. We don't know what is the interaction that develop, and so we have to come up with a sort of a displacement field, determine what kind of a force profile we get from LPILE, and then bring it back to limit equilibrium. So that is a completely made up story. There is no base for any of those things. The reaction of the element does not emerge organically from the interaction inside a complex system like we have in this case. But if we look at the single element, there should not be any difference as long as you compare apple to apple, meaning that if you're using nominal properties, you have to use nominal property for both. If you're using factor properties, you have to use factor property for both. I mean, at the end of the day, the integration of the domain that I'm using in FLAC 3D is coming from a simple sectional analysis in which I have the concrete and the steel and determine the truss bending diagram like you would do for LPILE. So the response is the same.
Great. Were you able to capture stress rotations and arching at the top of the rigid inclusions, or did the behavior resemble more like a pyramid between the inclusions?
Uh, that's a very good observation. I would say it depends on the relative stiffness of the embankment, and it depends on the height of the embankment. But typically, yes, one of the reason and also depend on the spacing, right? So you have to have a certain ratio so that you would be able to form that dome effect between. Yes, one of the reason for to implement those shell element at the top of the pile is to better capture this arching and dome effect that tends to develop. I didn't put it in my slide, but I have a slide in which I actually plot the principal stresses flow, and you can clearly see the dome effect going into at the top of the pile.
Okay. Next post is thank you for the presentation, very informative and inspiring. Question. Calibration of stiffnesses from CPT. How did the peat, how did the peat was dialed?
Yeah. So, as usual, it's a combination between science, art, and let's face it, gut feeling as well. So there isn't a comprehensive answer that is valid for every situation. But in general, the procedure that I tend to follow is the following. You have a CPT profile, better if you have a seismic cone for which you have the direct measurement of the shear wave velocity. If you don't, you can use several correlation, Robertson, for example, or Main, or others that gives you an idea about the shear wave velocity profile. From the shear wave velocity profile, you can estimate, knowing the density, what is the Gmax, okay, G0 for the soil, and therefore the Emax. Once we know the Emax, I tend to divide by 3 to get the E unloading reloading, not the reference. Keep in mind, not the reference, the E unloading reloading by 3.5 if it is a sense, even 2.5, let's call it 3. And if I'm in a clay, I tend to use 5. If I'm in an organic material, I tend to use even 8 or 9 to get the unloading reloading. And then from the unloading reloading to get the E50, I tend to divide by, let's say, 2.5 to 4, again, depending on what type of material are we talking about. The higher soil behavioral type, the higher the number that I use to divide the property, starting from the Gmax or Emax to E unloading reloading to E50. And then there is a separate conversation for the odometer. We didn't touch much into that. Keep in mind that when you're using rigid inclusion, that becomes secondary because essentially the rigid inclusion are shielding the volumetric deformation from developing in a significant manner. But if you don't have anything, that ratio between the E50 and E odometer, it could be in the order of 0.7, 0.75, all the way up to 1, or even a little bit higher for sands. That is a general guideline, but again, it depends on the site.
Okay. And then we have a couple questions that are the same. About how long did it take to run those models?
Oh, yeah, I was expecting a question like that. So, not much. Usually I tend to organize the run in such a way that I take advantage of the night, and roughly 8-10 hours would be ideal. Of course, in certain cases, that's not possible, especially when you go for dynamic time history analysis. It could take a week. But in this case, it was in the 8-9 hours to complete a full run. So it was not prohibitive at all.
Great, thank you. And then part of that question was what type of machine you used, and maybe I'll just add that.
Oh gosh, I don't remember.
Yeah.
I don't know the detail.
Our consultants typically use what we call a cruncher at ITASCA. We have a room full of them here in Minneapolis. So if you're interested in that, if you go to our website and look under FAQs, there's a FAQ for hardware recommendations, and we update it every year to include a detailed list of what essentially a cruncher is. for that year. So just go to our website under FAQ. I think it's even the first FAQ, and you can see that. Let's see. Hello, thank you, Augusto, for the interesting presentation. I would like to ask you if, in the case studies you have shown, you have investigated and assessed the possibility of substituting the rigid column concept with a piled raft concept to control lateral behavior of the foundation.
Yes. Actually,
sorry, Augusto, you're breaking up.
what's going on? Can you hear me now?
I can now, yes. Thank you.
So, yes, in a few cases, I've investigated, and I'm a proponent of that technology personally. In a few cases, I was able to break through. There is a sort of a, I would say, skepticism. I don't know for what reason. Instead of using this LTP with Geogrid, use a sort of a LTP made with lean concrete and maybe a mild reinforcement inside that would greatly solve all these issues and also simplify the construction, in my view. So the short answer is yes. In a few cases, I've been able, and I like that idea in general.
And then a follow-up to that was, if yes, which are the main structural, geotechnical, and economic outcomes of such assessments?
Again, it depends on the contractor. It depends on the site. In my view, it simplifies all the pile cap placing, all the geogrid, and you just create a working platform, and you drive down the columns or build a column in general, and then you lay maybe a net of steel net and pour lean concrete. And that's the end of it. So in my opinion, is optimizing the whole construction sequence. And it's still not to be seen as a pile and raft. It's still a ground improvement. The LTP, concrete LTP, is supposed to crack and essentially form natural pile cap naturally, and as it feels, depending on the engagement of the formation and stuff like that.
Great. Couple more questions. When should I consider that QA asymptote is equal to Q failure, QF, in the stress strain curve for hardening soil?
Oh, okay, so that is controlled by the failure ratio, RF. So all those parameters are somehow connected, okay? So essentially, if you're using a low failure ratio, the curves become stiffer, and the other way around. I tend to use an RF, which is in the order of between 0.8 and 0.9. So I tend to fix that parameter and then play with the other to get what I need. Otherwise, there are too much variable moving at the same time, and it becomes a little bit difficult. So I tend to fix the failure ratio, unless I have sort of a relatively stiff material like a rock or weathered rock or stuff like that. Then I tend to use a RF lower in the order even of 0.6 or 0.7 because otherwise I'm not able to get the stiffness that I want.
Cool. And let's see, next question. Do you recommend importing liners or creating them from zone faces?
Well, it could go both ways. When you have in this case, I generate the liner directly from the faces. So typically, it's worth, in my experience, if it's possible, to spend a little bit more time in organizing a mesh so that you can use the faces to generate the liner. It tends to work better. The liner needs to be a separation. So you cannot just randomly put a liner because otherwise you would not be able to capture, let's say, relative movement. if you have a liner, like for example, a D-wall, a diaphragm wall for an excavation, you're creating a cut in the soil. So that is a liner. You cannot model that with shell because you cannot generate a different separation. So in that case, it's just much simpler to use the faces to generate the structural element itself.
Great. And the last question for today, what modeling consideration were made to incorporate the installation stress and displacements of the ground improvement elements in the surrounding soil and rock?
Very, very good question. Again, there are several approaches that can be accommodated. In this case, for this large model, I just modify a little bit the keynote considering the installation. Keep in mind that the installation effect, that is part of the slide that I didn't show. Typically, you have a big spike of pore pressure, and then that pore pressure tends to dissipate. So you have a little bit of a consolidation horizontally, but in this type of material, it's not that much. It's not that relevant. If you have a loose sand, on the other hand, the horizontal densification that you're getting can be more important. Then at that point, I have two options. One is very important. I model the process explicitly. Essentially, I impose a strain related to the volume ratio of the ground improvement in such a way that I can modify the horizontal stress. Or simply, that takes a little bit more time though, because I have to do it gradually. I have to implement this process in such a way that I don't create perturbation. Or a simple one would just be to just impose a K-note. You modify the K-note after the model in equilibrium, essentially increasing the horizontal stress. Keep in mind that you have to do that also in iteration, because if you just impose a K-note and then cycle, the K-note tends to relax. So you have to have a sort of a control function that allows you to push the stress that you want, or you feel that the construction sequence has generated in the soil. In reality, we don't know how the stress develop and what is the importance. So we can guess based on strain or modify K-note.
Great. Well, thank you, Augusto, for your presentation and all the fine answers. Thank you, everybody, for participating and for your joining us today and for all your interesting questions. A recording of the webinar will be posted to our YouTube channel in a little bit. And if you've registered for the webinar, you'll get an email with a link to that. Also, quick note, I posted to the chat the link to our hardware FAQ if you're curious in learning more about recommended systems and what ITASCA is using. And then finally, if anyone's interested in speaking to one of our consultants, including Augusto, I included a link in the chat to a form, contact a consultant. And if you're interested in a free 2-week trial of any of our software, just let us know at sales@itascasoftware.com. Thank you, Augusto. Thank you, everyone. Have a good day.
Thank you, everyone. Thanks. Bye-bye.
Bye-bye.